So the first part is about the rate of reaction, frequency of collisions, effective collisions, non-effective collisions. Explain quantitatively in terms of frequency, the effect of concentration and pressure, and use experimental data to calculate the rate of a reaction. So the rate of a reaction is basically what it's any change that's happening with respect to time. And if that change happens very quickly, then that's a fast reaction. If the change happens very slowly, then it's a slow reaction. Usually rate is change in concentration over time. It could be the change in pressure over time, any change, a color change over time. You could have mass change, the volume of gas changing. So any change that happens with respect to time. Technically, it's technically change in concentration is used often, but not always. Okay, not always. It could be a change in mass, grams per second. How much is the mass changing? So normally it's change in concentration. But not technically, it should be usually it's change in concentration with respect to time. And the unit is usually it's mole per dm cube per second. Okay, but remember this thing could be different as well. It could be the volume changing, cm cube per second, etc. Now that is what rate is. First thing, how do you measure the rate of the reaction? The rate of the reaction is I mean, there's several ways of measuring the rate of the reaction. What can be done is that you can have, let's say I have an experiment, and in that experiment I've got magnesium, and it's reacting with HCl, and it's producing MgCl2 plus H2 gas. So what I can do is the volume of gas would be increasing. Because a gas is being produced. And usually it's going to increase in this way, that that it's going to normally increase in this fashion, that initially there's going to be no gas. So one axis would be time, it's always time, or the progress of the reaction, and the other axis is the volume of gas. And the graph is going to go like this. And normally reactions, they happen very quickly in the beginning and then they slow down. So the gradient of this graph of any change with respect to time graph. So basically, so what you're doing is you're plotting any change with respect to time. So that happens to be your change with respect to time. And the gradient of this graph is basically your rate at that particular point. Now the gradient continuously changes. Speed, like if there's a runner running a race, his speed is not constant. So the reaction speed will vary with respect to time. So the gradient of this graph is equal to rate. So all you have to do now is, if you want to measure the rate of a reaction, you'll just measure the gradient of any change plotted with respect to time. The steeper the graph, the faster the reaction, the bigger the gradient. So steeper gradient means faster. It means faster reaction. So I could have also plotted, what I could have also done is I could have plotted the mass of mg. The mass of mg must be decreasing with respect to time. Actually, clear is this? Is there any questions? So this one, what you could also have done is that the mass of mg it decreases with time. And again, what will happen is that if you plot a graph of mg or the mass of mg with respect to time, and the other axis would be time, then initially what will happen is that you'll have a larger mass, and then slowly the solid will dissolve. So the solid will start to dissolve and its mass would decrease. And again, the gradient would tell you the speed of the reaction. So right at the beginning, the gradient is really steep, and then the gradient becomes less steep. And if it flattens out, that means the reaction has stopped. So there are many ways of measuring the rate of the reaction. The best question that you'll probably get on this is, you've gotten questions like this in O-levels as well. They'll just ask you to actually measure the gradient. एक मैं वैसे ढूंढ लेता हूँ कि if I can, you won't. I mean, this part wasn't this. This was your O-levels. So I mean, this was your O-levels basically. You did the questions like these in your O-levels. This wasn't part of AS previously, but now they've actually added this. So you might be asked to plot. I mean, they might give you data. You'll plot the graph, and then you'll figure out the gradient at a particular time. They're going to ask you to measure the rate of the reaction at a specific time. Normally, it's measured in the initial rate is always measured. Initial rate is important for comparison purposes because every reaction slows down. So normally initial rates at t is equal to 0. So the gradient at t is equal to 0 is measured for comparison purposes. Because you can't really compare reactions like after 2 minutes because they might all stop. So it would be a pointless comparison because all reactions would have rate equal to 0 after 2 minutes. Which is why like if you want to figure out if you add Pepsi in a glass and you add 7-Up in a glass, and which one has a faster reaction, which one produces more bubbles, so you would want to measure the initial rate, not you wouldn't be measuring the rate of the reaction like after 2 minutes or 5 minutes. All the bubbles might have gone by that point. So initial rate at t is equal to 0 is measured for comparison purposes. So next one, hopefully this is clear. Okay, is this clear? Yes or no? Is this clear? आवाज आ रही है? अच्छा, next one फिर factors affecting rate, वो उसने that was the second thing. So what factors affect the rate of reaction? So factors में आ जाता है कि you've got there are two ways to describe a reaction. I mean, there's to describe collisions basically. So I've got these particles and they're trying to collide with not with each other. They're red particles and they're blue particles, and they're all going to bump into each other, and that's how a reaction will happen. And so these two are going to collide. So these two are going to collide, and then the reaction will happen. So reactions are dependent on collisions. Why do particles need to collide? Because old bonds need to be broken. So for example, if there's wood and you want to make a chair out of it, a new thing out of it, the first thing is you would have to break the old bonds in the wood. We would have to cut it into pieces and then you have to rearrange it. So old bonds need to be broken and after that new bonds are. So which is why collisions are really, really important. So what are the factors? And there were two ways of describing collisions. Number one is you describe it as you talk about the frequency. That is, how many times do they collide? So if they collide very, very frequently, that means it's a fast reaction. And the second way, it's the collisions are going to be described as uh, their effectiveness, or how strongly or how effectively or with how much kinetic energy do they collide. So if you imagine these particles to collide with each other with a very low energy, they probably won't be able to break the old bonds. You want them to really collide vigorously or with a lot of force so that the old bonds are broken, uh, because every reaction has some activation energy. So effectiveness is, are the collisions effective? Are they forceful enough? So pehla wala, number one, temperature. Okay, this is all O-level stuff. Number one is temperature. So what does temperature do? It increases the kinetic energy of the particles. And because of that, both frequency, now they're traveling faster, so they're bumping into each other a lot more, and because of that, because of higher kinetic energy, the effectiveness is also greater. So both frequency and effectiveness increases. That's a number two. Number two is pressure. As a pressure maker, you've got, and this is for gases only. Pressure is only for, it's only for gases. So at higher pressure, so what happens at higher pressure? At higher pressure, particles are closer to each other. If they're closer to each other, they're going to bump into each other a lot more. So higher pressure, volume decreases. As can be seen in the picture, you're increasing the pressure. So volume of the gas or the container decreases basically. So gas particles are closer to each other. And because of that, if they're closer to each other, there'll be more frequent collisions only. So the effectiveness does not increase. The particles are not, they're not energetic. The energy is not increasing. So they just bump into each other more frequently. So you get more frequent collisions. So the overall effectiveness kind of remains exactly the same. Pair number three here. Number three is concentration. So what is now concentration applies to, as remember, gases are the only things that are compressible. So which is why pressure is only for, this factor is only for gases. As coming back to concentration, concentration is a term that's used to describe solutions. and can also be described used to describe gases as well. Concentration is the number of particles per unit volume. So if I have two containers, so if I have two containers, and over here I just have three particles, over here I've got lots and lots of particles. So obviously this one is going to have a faster reaction. Why? More, because there's more particles. Higher concentration means more particles per unit volume. And remember to describe them, use the terminology properly. So higher concentration means more particles per unit volume. And so you're going to have more frequent. So you're going to have more frequent collisions. So you're going to have a lot more frequent collisions. Okay, you've got number 4. Let's talk about the fourth one. Is catalyst. बल्कि एक surface here कर लेते हैं कि smaller particles, smaller pieces have more surface area. More of this surface would be exposed. So you're going to have more frequent. So you're going to have more frequent collisions. And so obviously you have smaller pieces instead of one big lump. The particles inside the lump will not be able to react because the surface is not going to be exposed. So that is surface area, and again, you're going to have just more frequent collisions. And the last one is a catalyst. So a catalyst has, as a catalyst ka kya, number 5 is as the fifth one. The fifth one is a catalyst, and what a catalyst has is it lowers the activation energy. So that you have more effective collisions. So what it basically does is it makes it easier to break the old bonds. So for example, if you have N triple bond N and H2 reacting, and even if they're frequently colliding, there's not going to be much of a reaction because the old bonds are not going to be broken. The triple bond is pretty hard to break, so it's not going to be broken that easily. So what a catalyst would do is catalyst would make it a lot easier to break the old bonds. So catalyst makes it easier to break old bonds. Or what it does is it somehow reduces the activation energy, that the amount of energy that was needed to start the reaction because the reaction wasn't happening. So it somehow reduces the activation energy. That, I mean, you previously having 100 collisions, but now you're still having 100 collisions. Previously, only 5 of them were successful, but now 50 of them are successful. So what a catalyst does is it does not increase the frequency of collisions. It only makes them more effective. So ये सारा clear? This thing.
Yes.
So बाकी है कि now we're going to move towards let me catalyst wala kya hai? I'll explain a bit about catalyst. Explain that in the presence of a catalyst. The working of the catalyst is probably in it's still in A2. So you don't have to know how a catalyst works. Explain the presence of a catalyst reaction as a different mechanism. That is one of lower activation energy. Explain this catalytic effect in terms of construct and interpret a reaction pathway diagram for a reaction. अच्छा उससे वैसे कहा नहीं है कि यहाँ पे what is a homogeneous and heterogeneous catalyst, but I'm going to describe that. It's just one point. So I'll just briefly give you an idea, just a brief overview. There's a homogeneous catalyst. So one of them is a homogeneous catalyst. It simply means that catalysts and reactants are in the same phase. With phase, I mean the same state. So as an example, you've got the, one second. Okay. As for example, you've got homogeneous catalyst. It's simply it's the same state. For example, I've got the conversion of SO2 to O2 in the atmosphere. What happens is that it first reacts with NO2, and NO2 gets reduced to NO, and when it gets reduced to NO, the SO2 gets oxidized to SO3, and the NO again further gets oxidized back to NO2. So what is happening is, as a catalyst की expression जो चीज़ है वो that is it remains unchanged at the end of the reaction. I mean, speeds up the reaction. And it remains unchanged. So now homogeneous catalyst is an example. All of them are in gaseous phase. SO2 is a gas. Our catalyst NO2 is also a gas. So they're kind of all in the same phase. So that is simply homogeneous. They have the same phase or same state. Or उसका क्या होगा कि there's another one which is heterogeneous catalyst. So which is kind of the opposite. It's an opposite phase. Not opposite, different phase. So catalyst and the reactants have different they have a different phase. अच्छा अब इसमें one example for that would be I mean you've done a lot of reactions. It's very easy to identify. Like if you remember Haber process, all of the reactants are in gaseous phase while the catalyst is a solid. So they're all in gaseous phase, and you've got an iron catalyst which is a solid. So that is one example for that. So that's just a term that's frequently used. I don't think it's any long. I mean, I don't think that's any longer in AS. Because over here in the points they're not talking about homogeneous and heterogeneous, but we did this anyways. You be clear? Is this point clear? Yes or no? Is this clear?
Sir, I have a question.
Yes.
Sir, you said that catalysts don't take part in the reaction, but when we did nucleophilic addition, sir, the CN from the NaCN.
Then the first thing they do take part in the reaction. They remain unchanged.
Oh, okay.
वो लिखा हुआ है.
Okay.
I mean, sometimes they literally don't take part. Sometimes they take part. But the fact is that they remain unchanged at the end of the reaction. Okay, but I'll give you an example how a catalyst, like one catalyst. This is something that you'll do in A2, but I'll just give you just as an example how it reduces. There's a reaction of S2O8 2 minus plus 2I minus 1, and it produces 2SO4 minus 2 and it produces I2. Now this reaction is a very feasible reaction. I mean, everything about this reaction, if you react sodium with water, there's a reaction going to happen. The same thing applies to this reaction. It's a very feasible reaction, but it doesn't happen. And the reason for that is that both these ions are negatively charged. So if they're negatively charged, they're never going to meet each other. So think of this particle, and they both have a negative. They both have a negative charge. So they're never going to collide with each other. They're just going to repel each other. To make them collide, you would have to give them a lot of energy. You would have to give them a lot of kinetic energy so that they're able to overcome the force of repulsion because they're both negatively charged. So hence, it has a very high activation energy. So negative particles, they repel each other. And when they repel each other, because they're negatively charged, what a high activation energy, hence they have a high activation energy because you have to make them really energetic. So what you do is when you add a catalyst provides an alternate path for the same reaction. I mean, you're going to get the same products, but the route or the mechanism or the steps would be different. I mean, what they do is they add Fe3 plus as a catalyst. What Fe3 plus does is that it goes and reacts with 2I minus 1. The I minus 1 loses electrons, gives it to Fe3 plus. It becomes Fe2 plus. And and the I minus 1 gets converted to I2. That's step number 1. Then the same Fe2 plus, it then goes and reacts with S2O8 2 minus. And the Fe turns into 2Fe3 plus. And 2 SO4 minus 2 ions are produced. So what has happened is by adding Fe3 plus, the problem was, I'm just explaining how a catalyst works. These two ions were not reacting with each other because they were both negatively charged, even though the reaction was very feasible. These two things should have been formed. So what you did was, how did you lower the activation energy? You added Fe3 plus ions. The Fe3 plus ions went and reacted with I minus 1. They turned into Fe2 plus and I2 was produced. And then Fe2 plus that was formed reacted with S2O8 2 minus and turned into Fe3 plus and 2SO4 minus 2 was produced. As a result, you got both of your products from an alternate path. You got your I2 product and you also got your SO4 minus 2 product. These were your two products, right? And you got it from the same reactants. The I minus 1 got converted into I2, the S2O8 got converted into SO4 minus 2, and nothing happened to Fe3 plus. Fe3 plus, you started with Fe3 plus, it turned into Fe2 plus, the Fe2 plus turned back into Fe3 plus. So there was an alternate path through which you could have obtained the same exact product. But this reaction is a lot more feasible because now the particles are oppositely charged. Oppositely charged particles are going to collide or attract each other more frequently. Is that clear? The idea clear?
Yes, sir.
Okay, so remember, this example is not important. It's just an idea of how there are many ways in which catalysts function. Okay, there are many factors which hinder the speed of the reaction. Like in this case, both ions are negatively charged, so that is kind of stopping the reaction from happening. There are many other factors which affect the in the many different behaviors of catalysts. So that's just one example, which at least is not important at the moment. You might be asked about whether it's a heterogeneous or a homogeneous catalyst. So that you can kind of answer because all of them are ions and the ions would be in solution. So they're all in the same phase. I mean, this example. If Fe3 plus is the catalyst, then it's an ion. Ions are in aqueous solutions. These are also in aqueous solutions. So the reactants and the catalysts are all in the same phase. So this is an example of a homogeneous catalyst. Heterogeneous is when the reactant and catalyst have a different state. TK, is this clear? Is this clear? Yes or no? Is this clear?
Yes.
So now the very last thing, that's a new thing, TK. Remember, so far we haven't really discussed anything new. We've just did O-level stuff. We did the graph thing. How do you measure the rate of reaction? And so nothing new except for, this last part was, this one is obviously not in your course at the moment. That's A2. What is a homogeneous catalyst? What's a heterogeneous catalyst? You just need to have a vague idea of, not a vague, but it's a very specific idea, but it's a simple concept. The last thing is a Boltzmann distribution. The Boltzmann distribution is a way to describe molecular energies. इसके मैं spelling देख लूं. Boltzmann 1n 2n. ठीक है. So man, that's the last thing. Yes. So Boltzmann with 2n's distribution. Now, what happens in a Boltzmann distribution is that you have it's a distribution of molecular energies. A distribution of molecular energy. So and I'll just copy here. So this one second. This one, copy, let's say. I'll just hold on 1 second. Where's the board? Just 1 second. So you've got this container and it has lots of particles. And let's say the particles, this container is at room temperature, 25 degrees centigrade. Now, temperature is basically a measure of the average kinetic energy. It's kind of a scale that is proportional to the average kinetic energy of the particles. So if I say that this container is at 25 degrees centigrade, that doesn't mean that all the particles are at 25 degrees centigrade. What that means is that some of the particles, or on average, most particles are at 25 degrees centigrade or around 25. Some would have higher kinetic energy, some would have lower kinetic energy. Some would be slightly, because it's like billiard balls bumping into each other. So some would be traveling faster, some would be traveling slightly slower. But the average energy is coming out to be around or proportional to 25 degrees centigrade. So what a Boltzmann distribution does is that it plots the distribution of the molecular energies. So over here on one axis, you have your energies. That's your energy axis. And this other axis is the number of particles or the proportion of particles. Or you can also call it proportion or percentage, whichever you want to describe, or the quantity of particles. So let's say this is your average energy. Now, you'll have the maximum particles at average energy. So if I were to plot this point, the graph would be, the maximum number of particles would be on this average energy. Let's say that's 25. If I say high energy particles, how many particles do I have at very high energy? Then it's going to be very few. Because in this container, if the container, the average temperature, like if you're sitting in your room, the average temperature is 25, there would probably be very few particles that have energy that corresponds to 1000 degrees centigrade. I mean, that would be a very, very low probability. Maybe a few particles in the room, they might be bumping into other particles might be bumping into each other. So they might speed up a bit, or they might gain a bit of kinetic energy. But the probability of having a large number of particles at very high energy, that's very less. So the height is the number of particles. And the same thing for lower energy. At very low energy, the number of particles are going to be very few as well. Like if I say that I have particles in this container that are, or in my room at, let's say, minus 10 degrees centigrade, then there would be very few particles that correspond to that particular temperature. So at lower temperature, you'll have fewer particles as well. So the graph kind of looks like this. That if I plot the graph, it would kind of look like this. That at high energies, the number of particles would be lesser. At low energies, the number of particles would be lesser as well. But at average energy, the number of particles would be, there would be a lot of particles. At energy slightly higher than the average energy, you will still have a lot of particles. Or slightly lower than the average energy, you'll still have a lot of particles. Like if I say if my room is at 25 degrees centigrade, then not all particles would be at 25. Some would be at 26, some would be at 24, some would be at 23. The average energy is coming out to be corresponding to 25 degrees centigrade. But over here at very high energy, the number of particles would be very few, and at very low energy, the number of particles would be very less as well. Okay, is this part clear? You clear?
Yes, sir.
So remember, in a Boltzmann distribution, the peak kind of represents the average energy. Now, the other thing is, jo ki dobara, I think, so we'll do this. It's not described here. I mean, previously it was part of it. Maybe it's not explicitly stated over here. So we'll do this anyways. It's a simple thing. Now, what will happen to this graph if I increase or decrease the temperature? Okay, if I take this graph to let's say to a higher temperature. Now, let's say the temperature is, so now let's say temperature is, the new temperature is 50 degrees centigrade. So what will happen to the graph? what will happen to the graph is that the number of particles at having higher energy, that would rise because the temperature is higher now. The number of particles with lower energy, that would be lesser now. So the graph would actually go down from this side. Okay, so it will rise. The number of particles at high energy would increase because you're at a much higher temperature now, and the number of particles having low energy would decrease because obviously you're at a higher temperature. So the graph, the new graph would kind of get skewed to the right. And the average energy value would also, I mean, the peak would also shift to the right. Your new average energy is going to be a lot higher. It's going to shift to the right. The number of particles at higher energies, they would be more. So the graph would rise on this side, and the number of particles with lower energy, that would be lesser. So the graph is going to go down from this side. The right side, it's going to go up, more particles at high energy. Left side, it's going to go down, less particles at lower energy. And the peak would shift to the right as well because the average energy is now going to be much higher. It's corresponding to 50 degrees centigrade. So it shifts to the right as well. So is this clear? Is this idea clear? You clear? Yes or no?
Yes, sir.
Okay, similarly, you'll have another one, which is, let's say I decrease the temperature. So if I decrease the temperature, now what's going to happen? If I decrease the temperature, so at a lower temperature, you'll have more particles at lower temperature now. If I decrease the temperature, let's say I take the container to 0 degrees centigrade. And I have fewer particles at higher energy. So the graph is going to dip from the right side. So it's going to look something. It's going to look something like this. Let's quick. एक सेकंड में इसको सही कर लूं. So it's going to, the graph is going to dip from this side, it's going to rise from that side. And your new peak is going to be at a lower temperature, at a lower energy value. So this is how the graph would look like. And you get a lot of questions like this, that they give you a Boltzmann distribution, and then they ask you what will happen to the shape of the graph. So at a higher temperature, it flattens out a bit because the particles are now distributed over a much wider energy values. So higher temperature, uska likh dete hain. Well, I mean the picture, I mean, it's harder to describe in words. I mean, the picture is quite suitable, okay? So is this idea clear how the Boltzmann distribution works? Okay, lower temperature, more particles at lower energy, so that height would be much higher. And at higher energy, the particles would have less energy, so the height would drop. Ye clear? Yes or no? Is this clear? नहीं सारों को clear है? Aisha, Ruba, Lisa, Uncha, is this clear?
Yes, sir.
Okay, so that's about it. Okay, just remember that container will have particles at a lot of energies, very few particles at higher energy, very few particles at lower energy. Most of the particles would be, so the height is the number of particles. So most particles would be around the average energy. If the container is at 25, not all particles would be at 25. Some would be at 23. So a lot of them would be at 24. A lot of them would be at 25. They would be around the average energy. And if the temperature increases, then at higher energy, the number of particles would increase. It's going to, I mean, the graph would rise from this side, and at lower energy, the number of particles would be a lot lesser. and vice versa if the temperature decreases. So at lower temperature, you'll have a lot more particles, and higher temperature, the particles would be a lot lesser. So you get a lot of questions like this. The other thing that they're going to talk about is they're going to talk about kinetic energy, no, activation energy, catalyst. अच्छा, इसमें ये कि you've got this graph. Now there's going to be a point which would be called your activation energy. And let's say this particular point over here is your activation energy. So what is the activation energy? This end, this extreme right end, that is your high energy end. So what that basically means is that these particles over here, the height represents the height of the graph, represents the number of particles. So at high energy, you have these many particles. At this particular energy, you have these many particles. At this extremely high energy, you have these many particles. So these particles are the ones that can effectively react. Why? Because these are your high energy particles. They will bump into each other with a lot of force. So these particles can react effectively because they have energies that are greater than the activation energy. There's a point on this axis which is known as the activation energy. That is the minimum energy that is needed to start the reaction. So these particles over here, all these particles on the extreme high energy side, these are the ones are going to have effective collisions. So these are the ones that are going to have effective collisions as their energy is greater than the activation energy. As a greater than EA. Baki reh gaye ye wale. These particles over here, let's say this is the average energy. Okay, at this energy, you have these many particles. They're not going to be able to react effectively. Why? Because they have energies that are lesser than the activation energy. So they're not going to be traveling that fast. They wouldn't be bumping into each other with enough force. So their reactions are not going to happen. Okay, so out of all the particles in the container, there would be a lot of particles that would have, there would be very few particles that would have energies that would be sufficiently high enough. So not all of them would be reacting with each other. So if you have 100 collisions, a few of them would have effective collisions because they would have sufficient energy. So is this clear? Is the concept clear how to link EA with this Boltzmann distribution? Is this clear? Ye clear?
Yes.
I said, what does a catalyst do? A catalyst reduces the activation energy. So at the moment, the activation energy is over here. That's the minimum energy that is needed. So any particle that has energy that is greater than the activation energy or is at a higher energy, they're going to react. But what a catalyst does is it lowers the activation energy. So this is the new activation energy because it's lower now. That's with a catalyst. So now you don't need sufficient energy. I mean, the amount of energy needed to start the reaction, that's lower now. So now you have a lot more particles that are going to take part in the reaction. I mean, these particles were already effectively colliding. But now these particles would also be able to effectively collide. So the effectiveness of the collision increases. So if you have a lower EA, more particles can participate in the reaction, they can react effectively. Can effectively react and collide. ठीक है, तो बस ये, the only thing you'll get is you're going to get two types of questions on this. One is they'll ask you, I mean, they won't ask you to sketch this, but so one of them is that you'll be asked to plot the Boltzmann distribution or sketch the Boltzmann distribution at a higher temperature. The higher temperature, this is what the graph would look like. This would be the higher temperature graph. The other one would be you'll be asked to sketch or predict what will happen at a lower temperature. So more particles are at lower energy. So on this side, the graph would rise. On this side, at higher energy side, there would be fewer particles, so the graph would dip. And then they'll link it up with the activation energy. So there's going to be a point on the graph. Okay, after this point or below this point, the particles will not be able to react effectively because their energies would be very less. I mean, for example, these particles will not be able to react or collide because their molecular energies or their kinetic energy is very, very less. But these particles at the high energy side, they would be able to react because they've got a very high energy. If you lower activation energy, more particles can effectively react because you've reduced the minimum energy that is needed to start the reaction. So I think that's all there is. The questions are going to be, most of them are going to be very basic. We can try and do the questions probably in the next class, but it's just mostly.
Sir, what about Bronsted-Lowry theory of acids or something?
ठीक है, वो कल कर लेते हैं फिर, ठीक है?
Okay.
That's just probably it's just one line. I need basis using Bronsted-Lowry theory. Just a second. So if acids, strong acids, sex to do for pH will not be used here. So we'll do this. Explain the difference between strong. ये थोड़ा सा change किया है. This a bit of A2 is added, but it's basically still very basic. So we'll do that. We'll do that tomorrow then. ठीक है?
So this will be included in our mocks?
मैं देख लेता, it's not going to be included in your mocks. It's definitely not. मतलब ये अगर वैसे included होगा ना, ये तो बहुत easy है. मतलब पिछला वाला तो O levels है. इसमें तो
नहीं, but the mass spectroscopy and
वो भी नहीं है. नहीं, वो नहीं है.
Okay.
वो भी आसान है. उसका मैंने बस क्या कहा था, उसका बस you just have to, I mean, you don't have to remember the theory of it. You just have to remember okay, if there's an M peak, what does that mean? If there's an M+1 peak, you can figure out the number of carbon atoms by using a formula. If you have M+2, M+4 peaks, so you can figure out the number of chlorines and bromines. तो उसके अंदर बस वो question भी दिखाए थे मैंने कि वो बस simple, मतलब you don't need to know the concept or the design of a mass spectroscope. मतलब वो concept, no one is going to, it's not even in your course. The only thing is you just have to apply that formula. Okay, how do you figure out the number of carbon atoms? That's it. How do you figure out the number of chlorine and how do you figure out the number of bromines? ठीक है? Clear है?
Okay.
और बाकी मैंने लिखा है वो मॉक में. ठीक है? बल्कि AS के ना कोई भी क्वेश्चन में ना आज तक वो आया ही नहीं है क्योंकि अभी वो ऐड हुआ है. ठीक है?
Okay, sir.
चले. Okay, everyone, take care.
Allah Hafiz.